This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
around your HDMI.
Próximo.
Thank you very much for doing it.
Yeah, that would be oh, no, it's there.
Okay.
It's there.
I usually look at that clock.
Well, I'll be careful to look at that one.
At least one is working.
And it's about an hour?
About an hour.
Sure.
Welcome everybody to our now 6th gymnasium lecture. It's the last one in this series, so we had 6 in total. And we'll continue next year, maybe around March, with another small series. So keep an eye out for it on the School of Physics website or Google Eventbrite and Gymnasium lectures. Today for this lecture we have here Professor Harry Quiney with us. Harry is not only a professor at the School of Physics, but he's also the head of school. And his research area is in theoretical atomic and molecular physics and quantum chemistry. But I've also seen articles from him published in optics journals, radiology journals, synchrotron journals, and medical physics journals. So he's actually a true generalist with a wide wide range of research area. Today's lecture is about waves and particles, or light in general. So the question is it a wave or a particle? Let's see what Harry tells us. Thank you very much for coming, Harry.
Thank you. Well, thank you all for coming. I'm having a slight moment of deja vu because at 4 o'clock this afternoon, I gave a lecture to the second year class on precisely this subject. This lecture will be quite different to the lecture I gave to the second year class. And I shall be, let's just say, somewhat less mathematical than I was an hour and a half ago. But this particular subject is one which pervades really the whole of physics the whole foundations of certainly 20th century physics, the foundations of quantum mechanics, the foundations of the theory of electricity and magnetism, and it addresses the age-old question, light, what is it? Now, as I said, there's a teensy bit of maths, but it's very tiny. And actually, you don't need any of the maths to understand what I'm going to say. But for those of you who are interested, the only things that you're going to need to know is that there is such a thing as the square root of -1, despite what you may have been told. It's just a thing. So wherever you see I, I'm just talking about the square root of -1, the so-called imaginary unit. I need it only because there's a particularly important part of the theory of optics, which is this function e to the I theta, which involves sines and cosine functions. So the only thing you really need to know when you see e to the I theta is it's a combination of sines and cosine functions. There's the binomial expansion, which says that if x is sufficiently small, 1 plus x to the power alpha is approximately equal to 1 plus alpha x. So if something is very small, you don't have to work out its square root laboriously. You can just approximate it. And that simplifies the presentation a great deal and just makes our lives a good deal simpler. So to begin at the conventional beginning was the particle theory of light. This is largely attributed to Newton, and Newton argued that because shadows are cast by sunlight, that reflection occurs from smooth surfaces like mirrors and polished metal, that there's this phenomenon known as refraction of light passing from one material to another. He argued that this provided evidence that light was composed of particles that he called corpuscles. Now, Newton's research on light was published way back in 1704, which is actually considerably after the time that he did the research. And the reason was that Newton was apparently fixed in an endless battle with Robert Hooke. So at school you may have learned about Hooke's law and Hooke's law springs, and if I stretch a Hooke's law spring, then it will perform simple harmonic motion. Hooke and Newton did not get on, and they argued endlessly all those hundreds of years ago about what light was, what mechanics was, and such was the way of things back in those days. Newton did the only thing he could do, and he just waited for Hooke to die. So when Hooke died, he published this very thick book called Optics, which was Newton's theory of light. This theory of light prevailed for 100 years, possibly more, largely because Newton was famous, and for really no other reason. It wasn't a very comprehensive or well thought out theory of light, actually. It had an awful lot of flaws in it, but nevertheless, certainly in the United Kingdom in the 18th and 19th century, people believed it because it was by Newton. So Newton and mechanics, you could take it to the bank. Newton and optics, not so much. Newton and metallurgy, he was very seldom correct about that. Over in France, there was a far more comprehensive theory of light, which was proposed by Fermat. Fermat was a mathematician, these days mostly best known for Fermat's last theorem, which is that the only solutions of x to the n plus y to the n is equal to z to the n occur for n equals 1 or 2. The proof of this theorem took until the 1990s, and actually I can remember going to a talk that was given by Andrew Wiles, who proved Fermat's last theorem way back in the 1990s, and he got to the end and declared thus proving Fermat's last theorem, and even he was wrong, because about 6 months later he found a flaw in the argument, and then he had to go back to his office and find the flaw, which he did, and actually did prove Fermat's last theorem towards the end of the 90s. But in optics, Fermat is best known for the principle of least time. So the principle of least time suggests that light travels in straight lines, which these days are called rays, in a homogeneous medium. So we're talking about light traveling through one sort of stuff: air, water, glass, whatever. Now, the speed of the light traveling through this medium is a property of the medium itself, which these days we call the refractive index. And the refractive index has the property that the light travels more slowly in this material or at the same speed as light in a vacuum. So these days we say nothing beats light in a vacuum. That is the intergalactic speed limit of nature. But if light propagates through glass, then it travels a little more slowly. Now, in traveling through an inhomogeneous medium, or a medium consisting of interfaces, then the light will choose to go from point A to point B along a path which takes the least amount of time. And this was Fermat's proposition. And you can think of Fermat's proposition rather like the problem of a lifesaver at a beach. Imagine that there's a lifesaver on the beach at A, and there's a hapless swimmer down there at B. And medium A is running on the sand, and medium B, or medium 2, is swimming through the water. Now, obviously, it takes, you can run faster along sand than you can swim through the water, or at least certainly I can. Though I dare say Olympic swimmers, but who knows. Part of the skill in being a lifeguard is to decide where you're going to run to, the point P, such that you get from point A to point B in the minimum amount of time, given that you run across the sand at a different speed than you can swim through the water. This leads to a very familiar result. You can do the maths, but I'm not going to do the maths this evening, where you work out what point P minimizes the time going from A to P and then P to B. And the result of that calculation, given V1 and V2, the speeds of travel in the two mediums, leads you to the celebrated Snell's law of refraction, that N1 sine theta 1 is equal to N2 sine theta 2, so that if light goes through air and then travels into glass, then the ray of light will seem to bend in a direction which is determined by the relative values of the refractive index in the air and the refractive index in the glass. And you can carry on and solve all manner of problems this way. So, for example, the definition of a thin lens. Imagine I've got a source of light which is pushing out rays in all directions. I want to capture some of those rays, pass them through a lens, and make a parallel beam of light. In order to do that, I need to actually work out the time that it's going to take for the light ray to pass through the piece of glass and through the interface from, well, that's not very good. From the source along each one of these rays through the interface between the glass and the air, through the lens, and then out the other side. Now, in order to do that, you can do it in one of two ways. You can imagine that it works in reverse, that the light rays are coming in parallel and that they all have to meet this point F at the same time. You can set up equations for the time it takes to go from point F to the surface of the lens, which is described here by the curve defined by x, which is the thickness of the lens, through the lens and then out the other side. A little bit of mathematics tells you that x, which is the thickness of the lens, depends on the square of the radius measured from O to, say, this point here on the inside of the lens, which tells you that the outside surface of the lens is parabolic. If big R is the size of the lens, then the curved surface of the lens has to be shaped like a parabola in order to make all of the light rays going from F to a point on the surface and then out the other side take exactly the same time. So you can derive the shape of the lens from that principle. Similarly, you can ask the question, imagine that light is coming from, say, a distant star, and all of these light rays are coming along from, say, a distant star, so they're coming parallel. They have to bounce off the surface of the mirror and then all reach this point F at exactly the same time. Similarly, I could imagine having a point source, like a tiny little camera, a tiny little light source like this laser, shine the light and make it isotropic in this point, and make it such that all the light rays go to the surface of the lens and then all come out and reach this plane A here, all at the same time. Now, the mathematics for doing this is now almost identical to deriving the curved surface of a thin lens, and the ideal surface for making a mirror is also a parabola. So it's actually very difficult to make parabolic mirrors and parabolic glass surfaces, but if the lens isn't too big, and the parabola isn't, or the mirror isn't too big, then you can actually approximate this surface of the mirror by the bottom of a sphere. And the bottom of a sphere actually is quite a good approximation to parabola, provided that the angle that you collect light over isn't too big. And so you can make cheap lenses and cheap mirrors by taking spherical surfaces, because it's easy to manufacture them. If you want to build the Hubble Space Telescope, then you'd better make sure that this surface is precisely parabolic. And there are many, many examples of deriving optical elements, mirrors, lenses, and so on, all from the basis of the principle of least time. Now, probably the biggest single advance in the development of optics was due to Huygens. And Huygens developed a wave-like theory of light, which is ultimately the precursor to the modern theory. And actually, even though it was proposed in 1695, it contains many of the same elements that eventually were absorbed into quantum mechanics in the 1920s and 30s. Now, Huygens strongly believed, despite what Newton said, that the speed of light is finite, that things don't happen instantaneously, though that would have been impossible to measure way back in the 17th century. And he conceived of a model in which the light resembled pressure waves, but it was a wave-like phenomenon, not a particle phenomenon. Now, his results were incomplete, and they were kind of restricted to simple examples like reflection and refraction. But his general basic idea actually formed the basis for the theory of interference, the occurrence of diffraction patterns, and ultimately for the classical theory of light, which is based on waves. Now, this is where this pesky factor of I comes in, right? Because Huygens essentially said that every point where light is coming from is the source of one of these spherical waves. Think of a pebble in a pond. If I get a pebble and I throw it in a pond, then when the pebble hits the pond, that's like an impulse. But then the waves propagate outwards from where the pebble hits the pond in a series of spherical waves, spherical undulations. And you can see the wave fronts getting bigger and bigger and bigger, all emanating in 2 dimensions in circles, but in 3 dimensions in spheres. To make a spherical wave, well, you'd have to blow something up. If you can imagine having a small explosion in midair, then that will produce a wave that propagates isotropically in 3 dimensions. And this factor, e to the I kr, you'll remember that e to the I theta is cosine theta plus I times the sine of theta. E to the I kr is just a combination of sines and cosine functions, which actually capture this oscillating, undulating wave. The other thing which is important is that this wave depends like 1 over r. And so the farther you get from the place where you threw the pebble into the pond, the smaller the waves become, which is also an important part of the theory. So I've got waves undulating in space. I've got the amplitudes of the waves getting smaller and smaller and smaller. And then, according to Huygens, wherever I've got a wave, a generally shaped wave, then every point on that wave is making one of these spherical waves. And then each one of these spherical waves is propagating outwards, like the pebble in the pond, but now I've got gazillions of pebbles in the pond. Every one of these little pebbles all along the wavefront is each generating its own wave, and then I have to add them up. The principle of superposition, the idea that waves add up before you measure their intensity, is a pervasive idea in the theory of light. It's a pervasive idea in the theory of quantum mechanics. And ultimately, it says that there's a wave, but the probability is the square of the wave. And so the intensity that I see, or the probability of the wave having a certain amplitude, is equal to the square of that spherical wave u of r. And I can tell you that the square of e to the I k dot r in this sense is interpreted as being unity. It's equal to 1. And therefore, the square of this wave depends like 1 over r squared, which is the celebrated inverse square law. So phenomena that behave in this fashion, in which the thing that you see is the superposition of pebbles in the pond, generating spherical waves out through all space. The characteristic of them is that they are inverse square laws. So here is a schematic of my pebble in the pond. The origin is the place which is the source of the wave. The wave propagates outwards as a series of spherical surfaces, represented here as circles, and the distance between each one of the wavefronts, the crests and the troughs, is what we call the wavelength, which is lambda. And so in the theory of optics, different colors of light have different wavelengths, and therefore they have different frequencies. And so you can characterize particular electromagnetic phenomena by their wavelength. The wavelength that you see in the light, actually, if you get right down to it, is a consequence of how the light is made. So different physical phenomena will make light of different colors, because if you really get into where the light comes from, it comes about because I have a charged particle and I accelerate it. The origin of light is the acceleration of charged particles. And different atoms, when they undergo transitions, accelerate the electrons at different rates, and the different rates of acceleration cause different colors. That's beyond the scope of the lecture tonight. We're just interested in the light once it's made, not how it's made. But ultimately, how it's made is you accelerate charged particles. Now, Thomas Young played a particularly important role in the story of light. In fact, in his day, he played a particularly important role in the story of everything. Thomas Young is largely regarded, or widely regarded, as the last man who knew everything, back in the days when everything was a lot less than we know now. But way back in the latter part of the 18th and early 19th centuries, Thomas Young was interested in almost everything. Mathematics, all of physics as it was known then, mechanics, light. He was also a distinguished Egyptologist. He went to Egypt in the early part of the 19th century when it was opened up by the French expeditions. And he famously gave a demonstration of the properties of light and this idea of the superposition principle in one of the Royal Institution lectures way back in 1803. Now, the Royal Institution is a venerable place in Albemarle Street in central London, and every Christmas there's the Royal Institution Christmas lectures, and every year they have a sequence of public lectures that have been going all these hundreds of years. This one actually was the first public demonstration of light, The street just across the way, which is Faraday Street, Faraday was the great experimental master of electricity and magnetism at roughly the same time, around 1854. And I know this because Faraday Street is named after Faraday, who was active in 1854, who gave the Royal Institution lecture on electrostatics in that year, which is the same year as this university was founded. So all of the streets around here, Cardigan Street, Elgin Street is named after the Elgin marbles, which the English stole. Cardigan Street, Cardigan was a general in the Battle of Balaclava, which was fought on October 25th, 1855. But nevertheless, Thomas Young performed this experiment live to a rapturous audience in which he took 2-point sources, which made 2 spherical waves, and he did this by channeling light through a hole in the ceiling in the Royal Institution, and they turned out all the lights, and what they saw was this, that if you have 2 pinholes, you illuminate it with light from a distant source, then the waves from those 2 pinholes add up together, which makes a new wave, and then the intensity that you see is not the sum of the squares of the light, it's the square of the sums of the waves. So you get the spherical wave from the first pinhole and the spherical wave from the second pinhole, and you can see there's the first spherical wave, there's the second spherical wave. You add them at this point, so it's U1 plus U2, and then you square it. And this principle that you add light waves together before you square them to get the intensity is the same rule as the law of quantum mechanics, that the wave function that describes the mechanics of, say, an electron in a box or an electron in an atom, if you calculate any property of that system, say if you have 2 electrons, you get the wave function of the first one, the wave function of the second one, and then you square it. And so this linear superposition principle is evidence of the wave-like behavior of light, but it is also telling you something very fundamental about the nuts and bolts and wheels and gears of nature and how nature works. Now, Young's experiment, we won't do the mathematics here, but Young demonstrated by making some mathematical approximations that if I have 2 spherical waves and I add them together, what I expect to see is an intensity that depends on 1 over z squared, so it's an inverse square law. The farther away I put the detector, the weaker the signal will be. But the sums of the crests and the troughs of the waves actually gives you this squared cosine function, which means that I'm not going to see 2 bright spots from the 2 pinholes. What I'm going to see is some complicated pattern that comes about because the waves add, and then as I go across the screen, they will add and subtract in different ways, and so I will get a structure forming through the interference between the waves. And that interference pattern is described as being fringes, the fringes of darkness and brightness. The brightness comes about because of constructive interference between the spherical waves, and the dark bits are the destructive interference, where one positive part of the wave cancels out a negative part of the wave because I have to add them before I square them. So I have a positive number and a negative number. I add them and I get 0, and when I square 0, I get 0, which explains why I get regions which are 0, and where I have a positive number and another positive number, and I add them and square them, I get a positive number. And when I have a negative number and a negative number, and I add them and I square them, I get another positive number. So it's oscillating between 0, a positive number, 0, a positive number, 0, and a positive number. The occurrence of interference fringes is itself a manifestation of the linear superposition principle and the addition of waves. Now, the person who got all the ideas together and all the maths together was Fresnel. Fresnel was an engineer, and quite a young engineer actually. And there was a contest in, does it say, 1818. The French Academy of Sciences had a regular series of contests and challenges in science way back then. Fresnel was a nobody. Fresnel was 20-something years old and had only just graduated engineering school. And in those days, the French Academy had famous people: Poisson, Lagrange, Legendre, Biot, Savart, all of the great names in French science. And so essentially he was just ridiculed. You know, you're just a young kid, you don't know what you're talking about. So he entered, and in particular he was opposed by Poisson, who went on to develop Poisson statistics and the Poisson equation, which is the equation of electrostatics. And he made a prediction. And we'll discuss the prediction in a moment, but this prediction was tested experimentally by Arago. And Arago went on to become the president of France shortly thereafter. So Arago was himself very distinguished. And if you see the movie, that Dan Brown movie, there's the Arago line, which passes past the Louvre. So he put in his application to win the prize. He challenged the French Academy to test his prediction, and he won. Fresnel won. And everyone was very cross with him because, you know, who was this upstart young engineer guy telling us what happens? And, you know, essentially his prediction was apparently ludicrous. But when they tested it, it wasn't ludicrous. It actually worked. And at first sight, it seems a little surprising, but this is what happened. If you believed in the particle theory of light, and let's just say I have a stream of light particles coming in a particular direction, and I have some little circular opaque screen. Imagine a very tiny coin. Then what you would imagine is that the light would merely cast a shadow onto the wall, because the coin would stop the light, and all the light that passed the coin would just go onto the wall, and I'd see a black spot. But what Fresnel predicted was that no, the situation would be much more complicated than this because of this idea of the spherical waves. If I have the light passing past this obstacle, then every plane of light as it's passing through the entire system is itself the source of spherical waves. And so from the wave point of view, Fresnel said, okay, well, everything's going to be fine and dandy before it hits the little coin. But at this point here, right, it's going to make these spherical waves. And ordinarily, if this coin wasn't here, a point here would make the spherical waves, and they would all add up like they did here to make a constant wavefront. But by stopping the spherical waves being produced here, a spherical wave that's generated at that little point there actually starts to go around the corner. And there's nothing actually to counteract it, because there is no light here that would add up to give you one of these nice straight lines. So the idea is that at the very corners, just outside the coin, the spherical wave has a certain amount of curvature. And then as it propagates forward, it actually starts to impinge on the area that would otherwise be blocked out by the coin. And as it goes further and further, you can see that these spherical waves actually make their way into the region, which you can think of as the forbidden region. And so this forbidden region, which would be forbidden by the particle theory, is not forbidden to the wave theory. And so the spherical waves all turn the corner, and if I have to add them all up, I would reasonably expect that there would be the superposition of a lot of waves all gathering along that axis, which was Fresnel's prediction. And Fresnel went further, and he estimated exactly how intense the light would be along the z-axis, and he came up with this formula where z is the distance Z is the distance, yeah, this is not at all good. Z is the distance from the coin to some point along that axis, and A is the radius of the circular aperture. And you can see if Z is 0, then the intensity is 0. So if I'm way back just where the coin is, the light doesn't have enough opportunity to curl around the edge. But after Z is quite large, if Z is much bigger than A, then Z squared over Z squared plus A squared tends towards 1, if Z is much bigger than A. And so along the line, Fresnel predicted that you should see a spot. The superposition of all of those waves when you square them, which should actually produce a spot along the axis, and that the spot should have the same intensity as the intensity of light on the left-hand side of the aperture. So they measured it, and these days you can make quite a nice picture of it, and this is what you actually observe. What you observe is a series of ripples outside the forbidden area, which is the superposition of the spherical waves kind of diffracting off the edges. But you also see the build-up of intensity along the z-axis, because the waves are able to curve around, enter the forbidden zone, add up, and when you square them, you see a number which is very different to 0. So you don't see a shadow, you see the spot. And this is the famed spot of Arago. It's also somewhat mischievously sometimes called the Poisson spot, only because Poisson ridiculed this idea so much that for 20 or 30 years afterwards it was called the Poisson spot, simply to humiliate Poisson. Now, a focusing lens, we've already know that a spherical wave, if I'm quite a long way away from the focus, behaves like a spherical wave, and the mathematical form of that is that it's like a set of sines and cosine functions depending on the square of the distance from the optical axis. So that's telling you what it's like to have a point source and generate a spherical wave. But I could reverse that. If I have a uniform illumination and I pass it through a lens, I can make all of that light focus down onto a point. So the whole idea is reversible. If I have a point source and it propagates outwards, it generates a spherical wave. If I have a plane wave and it goes through a lens and it focuses, then the change in the phase going through the lens has to be the same going backwards as it was going from the point source to the plane of the lens, because the equations governing light are entirely reversible. And so what this tells you is that if you work out what happens to the light as it passes through the lens, because of this factor e to the minus I pi rho squared over lambda f, all I'm really doing is changing the relationship between the sines and the cosines. I'm putting in a phase shift. And that turns out the solution of that equation is exactly the same equation as the one that was generated from the principle of least time. So the principle of least time predicts that the shape of a simple lens should be a parabola. If you work out the phase shift of passing light through a simple lens, it imposes that phase shift on the light as it passes through, and that causes it to focus. So the two ideas, there's no winner yet, right? The particle theory and the light and the wave theory are both coming up with identical predictions about the lens. Now, also in the middle of the 19th century, James Clerk Maxwell came up with his famous equations for electricity and magnetism. There are 4 of them, and essentially they tell you about the relationship between charges and currents and magnetic fields and electric fields. Maxwell proposed that light traveling through space was a wave, and it wasn't, and you might ask, a wave of what? And the answer is it's a wave of electric fields and magnetic fields, where the electric fields and magnetic fields are perpendicular to one another. The electric field generates a magnetic field, the magnetic field generates electric field, and so there's this squeezing of energy as it passes, propagates through space. The equations are very beautiful, but we're not here tonight to discuss the equations, other than to note that we know from the middle of the 19th century that light is not just some magic, it is a phenomenon associated with electricity and magnetism, which before Maxwell was largely associated with lodestones, magnetic materials, static electricity. Maxwell brought all of these kind of reasonably well-known electromagnetic phenomena under one umbrella of four equations. If you look at diffraction from a pinhole, a single pinhole, what does it look like? What it looks like is an intensity pattern which is strongest in the forward direction, but you have these zeros. My laser pointer's giving up the ghost, unfortunately. Oh, there we go. You have these series of zeros there and there and there. You can write down the equation for this wave that comes out of a pinhole. It's a rather complicated function called a Bessel function, which we need not worry about. But the way of thinking about it is that it gives you a set of concentric zeros. So it's positive intensity quite strong in the middle. Then there's a zero, which means that all of the phases add up to give zero, and there's destructive interference on a circle. And then there's a bit more intensity out here on the wing, right there. And then it goes through another zero, and then there's a little more intensity, and it goes through zero. So there's a series of circles, which are zeros, and a maximum intensity in the forward direction, which from a simulation actually looks like this, that you have a very strong central part, zeros, and then rings, so-called airy rings. Now, here is one I produced earlier. This is experimental data from the Australian synchrotron, and it was obtained from a pinhole, a real one, by shining, I think it was 900 electron volt, 900 eV photons, which is ultraviolet light, onto a pinhole. You might wonder what this black thing is here. The black thing is because detectors cost about $500,000. And the beam of light going through the pinhole, as I said before, in terms of the idealized diffraction pattern of a pinhole, is incredibly bright in the middle. So if you shine the beam of light through a pinhole, it's still very bright along the axis, and you will actually blow up a $500,000 detector, and the people in Clayton will be very cross with you. So in order to get around that, you have to stick this stick, which is actually gold. And the gold actually absorbs the light, stops it from blowing up the detector, and you can see the rest of the diffraction pattern. Now, this is just one frame. In fact, this is collected on 1 second. So this is as much information as you get in 1 second. And it kind of sort of looks like what I described, in the sense that you see these concentric circles, but way out here, you don't see circles at all. You just see individual blobs. And each one of those individual blobs is one photon, right? One photon is absorbed by the detector, not an entire airy pattern, not this continuous wave. You actually collect the photons one photon at a time. And so if I had the exposure for less than a second, it would look terribly noisy and the rings would be incomplete. And if I look at a different frame, you can see I get a different answer. Right? So I'm not getting the same answer every time. And in the region which is black and red, I can see an awful lot of change from one snapshot to the next snapshot, because each one of those little bits of red is one photon that's been absorbed by the detector. And then there's another frame, and then there's another frame. So you can see every one of these 1 second exposures is different, and it doesn't really form the perfect circles, and it doesn't really form the zeros and the maxima very smoothly. But if I add them all up, then I get this. And now I have nice complete circles, and the nice complete circles go out a long way. There is, because this is a real experiment rather than some idealized thing, it has other interesting features. You can see these kind of crinkly bits here, right? So there's a sort of structure, and you might wonder what the structure is. It's because it is unbelievably difficult to make a pinhole. You would think, how hard can it be? But for the wavelengths of light that we're using, any little imperfection on the edge of the pinhole causes this kind of rough, unidealized behavior because the light gets caught on the little jagged edges of the pinhole. And despite our best efforts, we made the pinhole by blasting a laser through it. We etched it with acid. We did all the right things. But nevertheless, this was the best pinhole we could make because there is no fooling nature. So, diffraction from a pinhole. The X-ray diffraction is actually very weak. We do not record the predicted Airy pattern. Every one of those 1 second exposures is not the nice smooth wave at all. It's a collection of individual dots. When you add them all up, the average over adding up all of those frames does make the nice smooth diffraction pattern. But every individual snapshot, if I took a snapshot that was 1/10 of a second, it would look even worse. And if I took one which was 100th of a second, well, you might only see 50 or 60 photons, so you just see a few red dots and no structure at all. So something else is going on here. Light does not behave like a wave in nature, because if it really did, then for every frame, all I should see, if it really were a wave, is just a fainter version of the entire Airy pattern. And if I do it 10 times, I should get the same result every time. And when I average it all up, I should get the same answer, but I should see none of this granularity. I should see no evidence of detecting individual photons one at a time. And so what I actually see, and that's what I actually saw, because I actually stayed up all night doing the experiment, is one photon at a time. So yeah, the answers on average may add up to the wave theory, but the experiment doesn't behave like that. So the wave theory of light actually predicts a probability distribution. It doesn't actually reflect how the thing is working from moment to moment. It is the long time average of the probability of light appearing in particular points on the detector based on the wave theory. But I could, if I wanted to, and if I were happy to stay up for 2 nights in a row, and it's very bleak in Clayton in the middle of the night, so I wouldn't want necessarily to do that. I could, in principle, fire 1 photon at a time. And these days you can do that. There is such a thing as a source that will make 1 photon at a time. And I could fire 1 photon through the pinhole. And what am I going to see? I will see 1 blip on the detector, and that's it. And I could fire another one, and I will find another blip on the detector, almost certainly somewhere else. And I could keep on doing this. And indeed, this has been done. About 15 years ago, they developed these 1 photon sources just to verify everything that I'm saying tonight is true. Right, that actually the probability distribution is determined by the wave theory, but the physics behaves like 1 photon at a time. I throw the photon at the pinhole goes, the photon goes somewhere. If I do it a gazillion times, the statistical average over the experiments builds up the expected intensity pattern. But the evidence does not support the idea that there is a wave that propagates majestically to the detector, and that the square of that wave is what's detected at the detector. Oh no, it's 1 photon at a time. So light is not, in fact, a classical particle, because if it were, then I should see a very faint, complete diffraction pattern for every photon that I let go. But actually what I see is a series of individual events. Light is not a classical wave because we observe that light is detected photon by photon. And diffraction patterns are a measure of probability, but not really a reflection of the intensity of the classical wave. Now the other thing, yeah, and I've got time. The other thing I want to mention is the photoelectric effect. which tells you that photons carry energy. The photon carries energy in an amount which is proportional to its wavelength or its frequency. And if you perform the experiment and I shine light on a material such that when the light is absorbed, it throws an electron out, then the energy of the electron which is thrown out is equal to the energy of the photon that you put in, minus the amount of energy it takes to actually take the electron out of the material, the so-called work function. This tells you that the energy is quantized in packets. One photon carries the amount of energy h nu, or h bar omega, and that it's an all or nothing event. The photon goes in, and either nothing happens, and the photon just reflects off the surface, or the photon is absorbed, and that energy is transferred to an electron which gets thrown out. It's all or nothing, right? There is no half a photon or a third of a photon. There is no kind of sharing between friends or anything like that. It's all or nothing. So Einstein won the Nobel Prize for the photoelectric effect, not for Brownian motion, not even for the theory of relativity, for the theory of the photoelectric effect. And he interpreted this observation of the photoelectric effect is that the light behaves like a particle, and that the energy of this particle is h nu, and that the atom has to absorb or emit an entire photon, all or nothing. It either takes it and gives it a home and throws out an electron, or nothing happens. The photon just passes through the atom and nothing happens. And this is actually what Einstein won the Nobel Prize for in 1921. Not for the things perhaps that we think of him today, particularly general relativity, special relativity, but for the photoelectric effect and for the suggestion that the photon is a particle. Now, he had a lot to say on this throughout his life about the so-called particle-wave duality. And way back in 1924, when he was still fairly young, he said, there are therefore now two theories of light, both indispensable, and as one must admit today, in spite of 20 years of tremendous effort on the part of theoretical physics without any logical connections. Right? That essentially in 1924, there were two theories of light, and you kind of picked and chose which theory of light seemed most appropriate to the particular circumstances that you were talking about. And then in 1954, shortly before he died, he memorably said, all these 50 years of conscious brooding, I love that phrase, conscious brooding, have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick and Harry thinks he knows it, but he is mistaken. And since I'm Harry, I wouldn't dare to contradict Einstein. And it's still true, right? There is no really comprehensive explanation in words or terms that make any sense at all that resolve the mystery of quantum mechanics, the problem of quantization, or the physical explanation of the subatomic world. We know the rules, and we're very, very good at the rules. And if you were to come to the School of Physics and study physics, then we will give you an excellent education about the rules of quantum mechanics, which apparently have absolutely infallible predictive power. They work. The laws of quantum mechanics work. All the rules that I've told you tonight are the Reader's Digest version of the rules, and they all work. Can I explain to you the origin of those rules? No, I cannot. And neither can anyone else, Tom or Dick or any other Harry. The other memorable quotation on this was by Bragg, who was sometimes claimed as Australia's first Nobel laureate, though actually he was from Manchester. Physicists use the wave theory on Mondays, Wednesdays and Fridays, and the particle theory on Tuesdays, Thursdays and Saturdays. And obviously no one is a physicist on Sundays. So, is it a particle or is it a wave? Well, my colleagues on the third floor are the community of particle physicists. So the particle physicists will say unequivocally that it's a particle. And indeed, the way we think about it is that there are quanta and that they are individual units. And insofar as we understand the current state of fundamental physics, then there are particles which are the particles of matter, there are the force carriers, the so-called quarks and leptons, and the gauge bosons, and the Higgs boson, which gives particles their mass. The photon, gamma, is one of the constituent particles of this so-called standard model. And the only thing that we know about the standard model is that it's probably not complete, because there is abundant evidence that there are parts of the universe we don't yet understand, particularly the concepts of dark energy and dark matter. As far as we know, there are particles which exist, and maybe they only exist through gravitational interactions, which is going to be a bit of a shame for the people looking for them, using interactions with ordinary matter. But insofar as we understand the underlying structure of physics, the particles are quanta. They carry discrete units of charge, or units of energy rather, and that they have probability distributions that we calculate essentially using some form of wave mechanics. Now I'll leave it tonight, I've still got a couple of minutes, I'll leave it tonight with the greatest theory ever made, which is quantum electrodynamics. It was kind of the first of the unified theories that connect matter and radiation, electricity, magnetism, and charged particles. And quantum electrodynamics was started in the 1930s at the same time as quantum mechanics hit. Most of its kind of most important difficulties were addressed in the 1940s and 50s. And although actually doing quantum electrodynamics is quite mathematically formidable and something you will only do if you come here and, say, do a master's degree, the rules of quantum electrodynamics, which is about charges and their interactions through photons, are surprisingly simple. There are actually only 3 rules. Rule number 1, a photon travels from A to B along every possible path, right? So the wave-like behavior of subatomic particles tells you that trajectories are out, right? That they don't go in straight lines between A and B. They have to go through every possible path between A and B. And each one of these paths is associated with a thing called the probability amplitude. And what you have to do is to work out the probability amplitude for every one of these paths, add them all up, and then square it. So it's not so much waves as this slightly more generalized idea that every path that connects A to B is associated with a number. You add up all of those numbers, and only when you've added them all up, then you square them, and the square of it gives you the probability. An electron does the same thing. An electron goes from A to B along every possible path. Every possible path is associated with a number. You add up all the numbers that are associated with each one of the paths, and then you square it, and that gives you the probability of going from A to B. And then the third rule is that electrons and or positrons interact with photons either by entirely absorbing a photon or by emitting a photon. There is no halfway house. It's all or nothing. The photon either goes in or the photon comes out, but you don't have a photon. It doesn't give it half its energy and then make another. None of that happens. It's all or nothing. And so the probability of any of these physical processes comes about by summing up all of these numbers associated with all of the paths, summing them all up to look at every contingency, and then squaring the answer that you get to give you the probability of a particular event. And so the mathematics for doing that is very formidable and takes quite a long time to learn. But that is, in essence, the fundamental physical basis of particle physics, quantum electrodynamics, all of the complicated physical theories behind the standard model. They are all variations on that theme. And all of them are consistent with everything I've told you tonight about light, right? That there is a wave, you can think of it as a wave. The wave is a mathematical object which is really the sum over all of these paths. By summing up all of the paths and then by squaring them, I get the same answer on average as the wave-like formulation of light. But the thing that I know from experiment is that a particle goes from A to B like a photon, either entirely or not at all. The photon is either absorbed at P or it goes somewhere else. It's not shared between locations. So I think that's as much as I want to say on that, because I've run out of time, except for a summary. The behavior of light has actually guided physics for more than 400 years. Started with Newton, Huygens, Fresnel, and there have been incremental advances in the theory of light over all those years. But ultimately, it comes down to this basic idea that every point in space where there's light or electromagnetism is the source of a spherical wave. The spherical waves add up. When you add up all the spherical waves, then and only then do you square the answer to give you the probability. If there's no diffraction, then the ray-like behavior will be fine. So light through a lens, diffraction is negligible, the ray theory will do just fine. Diffraction suggests this wave-like behavior, but we observe individual particles of light arriving in the detector, like the data that I showed you earlier. So we will still see a diffraction pattern, but only if we take a large enough sample. It's a probability distribution, and to see the probability distribution, you have to perform lots of experiments. The photoelectric effect, which is what Einstein won the Nobel Prize for, tells you that each light particle is carrying energy, and that energy is quantized, and that the energy that a light quantum carries is proportional to its frequency. Light is ultimately described by probabilities. The probability that it goes from A to B is the square of a certain number that you can calculate with enough background in maths and enough patience. And at a fundamental level, the behavior of electrons and all the other particles, all those particles in the standard model, all work according to laws which are variations of the laws we discussed today. There are probability amplitudes, there are rules about the interaction between the particles and the particles that are used to communicate between the particles, the so-called messenger particles or force particles. But ultimately, at the subatomic level, all of this light, electrons, all works according to the laws of quantum mechanics, and that quantum mechanics is pervasive, and that it fuels a lot of the research that occurs in the School of Physics, and it remains both a conceptual challenge but also a technological challenge. You know, that quantum mechanics is underlying the development of quantum computing and quantum sensing and new technologies and even AI as we speak in this building. So thank you very much for your attention. Any questions?
Hey, sorry, you said due to the photoelectric effect, you either absorb the photon and lose the electron, or you don't.
Or nothing happens.
Happens, right? That means photons ionize if they have enough energy, correct?
Yep. Yeah, but if you don't have enough energy to ionize it, then you can make an excited state, but then it will give off the energy again. And the energy will be absorbed in a lot of complicated processes, vibrations, and other things. This is a fairly idealized experiment.
Then how does the photon gain enough energy as the sun emits photons, right? Mm-hmm. That means if a normal photon would have enough energy to ionize, it would be harmful to us. So how does a photon gain energy? How does it gain energy?
Oh, how does a photon gain energy? It goes back to what I said. It's not really part of the talk, but you have to understand how photons are made. A photon is made by oscillating an electric charge. So how is this light made? How is the strip light in the ceiling making light? The answer is that a current is passing through a gas. The gas is actually, the atoms in the gas are going into an excited state because you put energy into them. And then because they're in an excited state, they drop down to a lower level, which then causes the emission of a photon. And that emission comes about because the electrons in the atom are actually accelerating. And they're accelerating because they're experiencing a force. So if they were in their ground state, the total force on the atom would be zero because it's at equilibrium. If you put the system out of equilibrium, then the electrons in the system experience a force, and the force which they experience actually causes them to accelerate through Newton's law, if you like, and that acceleration then causes the emission of light with an energy that corresponds to the energy difference between the excited state and the ground state, typically. So how do I make light with enough energy to cause photoionization? Well, typically I would do that. I would use a sort of atom that produces light that has a higher energy than the work function of the thing I'm trying to ionize. So the experiment famously, the one that Einstein got the Nobel Prize for, was, I think, sodium. And it was a piece of sodium in a bell jar in a vacuum. It's a difficult experiment to do. It's surprisingly difficult. The reason it was 1921 rather than 1905 was it was a very difficult experiment to actually make it work. And the reason is that sodium oxidizes very quickly, and when you make a nice clean surface for the electron to come out of, you have to somehow prepare this under vacuum itself, because if you just cut it with a knife, and you can cut sodium with a knife, it immediately becomes a mixture of sodium and sodium oxide and sodium hydroxide and various other stuff. But basically, if I have a light source that comes in of a particular frequency, then it will liberate one of the outer electrons of sodium, which is the 3s electron, and the binding energy of the 3s electron in sodium is a very small number. It's electron volt or two. So provided that the energy of the photon coming in has an energy bigger than an electron volt or two, then the energy of the electron coming out will be the energy going in minus the energy of the binding energy of the 3s electron of sodium. So the conservation of energy law, it's inviolable. Not even the head of school is allowed to break it. Yep.
I had a follow-up question from that. So I understand that when you have an electron in the excited state and it gets kind of accelerated down, that causes the emission of the photon.
Yep.
How can we use, like, why can't we use that for if a photon hits the electron of the perfectly right energy? Doesn't that also accelerate the photon up? And isn't that an acceleration?
Yes, and you can.
Would it emit light as well?
Well, not necessarily. It depends on the energy of the photon coming in, because you can think of this as a sort of ladder, and the energy levels get closer and closer together, and this is E equals 0. Now, in the case of sodium, the electron configuration is 1s2, 2s2, 2p6, 3s1. So there's 2 electrons there, there's 2 electrons there, there's 6 electrons there, and there's 1 electron there, and that's called 3s. And the energy gap between that level there and there equals 0 is, let's call it 1 eV. I don't know the number off by heart, but let's call it a small amount of energy. And then a photon comes in with an energy E equals h nu. It's absorbed by this electron and then ejected outwards. The energy of the kinetic energy of the electron which is ejected is the original energy, which is h nu, minus this amount of energy, which is what's called W. It takes an amount of energy W to get you from there to there, which is E is equal to 0. And E equals 0 corresponds to an electron at rest. That's an electron which is just an electron sitting there doing nothing, minding its own business. This electron, however, has absorbed the energy of the photon, and it's also overcome this energy gap here, which is actually due to potential energy. The electron is trapped essentially in a potential energy well, and you need to give it enough energy to get over the top of the potential energy well. And then all the energy which is left over is kinetic energy. Okay?
My question was more like, so the electron has been accelerated
Yep.
from where it is.
Yep.
You said before that accelerating charge will produce an electromagnetic wave.
Mm-hmm.
Why would this? I understand, of course, like energy
Uh-huh.
conservation is going to have kinetic energy. But in this acceleration of an electron,
Yep.
why is there no photon produced?
Why is there no photon produced? Well, there's a difference between absorption, emission, and scattering, right? So let's just say I have an atom, and I have light coming in this way, and it's oscillating with a certain frequency, nu. And this atom has a positive charge and a whole bunch of negative charges. And I said, we had the slide about Maxwell's equations. What is this? This is an oscillating electric field, where the electric field is oscillating, say, in that direction. For various complicated reasons, if the photon is going in that direction, then the electric field is oscillating in a direction which is perpendicular to the direction of motion. And yes, it is completely true that the electrons in this system here will respond to this oscillating electric field. They will absorb the light, and then they will re-emit the light. So if I have the light coming in here, and this is an atom, and the atom doesn't change its state, so there's no absorption caused by the oscillating electric field, what will happen is that it will produce another photon, and the direction of the photon, there's a probability distribution for that as well, but the oscillation and the charges inside the atom in here will produce another ray of light, typically not necessarily in the same direction. And so there will be a probability distribution as a function of theta, and that process doesn't produce, it doesn't seem to produce anything because it entirely absorbs the energy here and then re-emits it there. The conservation of energy says that this also has a frequency nu. This goes back to its ground state once the photon is produced, and the only thing that happens is that there's a change in the momentum. And that change in the momentum, if the photon is going that way, there'll be a recoil of the atom which will actually move down in that direction. So the conservation of momentum has to be conserved, the conservation of energy has to be conserved, and if there's no change in the state of the atom, then the amount of energy in the photon coming in has to be the same as the amount of energy going out. And that entire process is called scattering. And scattering is the tool that we use to look at atomic structure. So if you want to know about how molecules are made, this is how you do it. You basically get your molecule, you fire X-rays or electrons at it, and then this is your probe, and this is the recoil target. You then have a detector that detects the secondary particles which are emitted, and the probability distribution of these photons tells you about the internal structure of this atom here. And actually the thing that determines the angular distribution here is the electron density. So the scattering of light is actually proportional to the electron density of the atoms that cause it. And atoms behave like slits. If I have two atoms, each one of those atoms will also produce a spherical wave, and then the two spherical waves will interfere, and then I will see a diffraction pattern.